Hello, and welcome to application session 4 of this Introduction to Linear Algebra with Wolfram U. The topic for the session is data compression. So let's begin with a brief overview of the session. So what is data compression? Well, data compression is a reduction in the number of bits needed to represent data. So if you have some data, then that consumes a certain number of bits in storage, and what you'd like to do is to somehow reduce that number of bits, and that's what is called data compression. Now, the nice thing is that a lot of real-world data can actually be represented in terms of matrices, which has been the theme of this course. So, for example, 2D or 3D images in the Wolfram language correspond to matrices in some sense. Sometimes there's a bit more general matrices, but basically matrices are good enough for representing images in the Wolfram language. Now, why is that important for us? Well, in the last lesson, we talked about the singular value decomposition of a matrix, the SVD as we'll call it. And so if we put it all together, then hopefully one can use the SVD to somehow do data compression. So the goal of this session is to show how the SVD can be used to achieve data compression for an image. So let's begin by talking about how you can represent a matrix as an image. So suppose you have a matrix with entries in 0, 1, a square matrix, let's say, then the image function in the Wolfram language will let you generate an image from it. So here's a 3 by 3 matrix with entries in from 0 to 1, and you can generate an image, in this case a black and white image, based on this matrix. So the entries over here correspond to the colors over there. Okay, you can do the same thing for RGB, red, green, blue color images, but then you need a slightly more general object in which at every pixel basically you have the RGB values. So here is an array, not just a matrix, and you can once again generate a nice color image from it. And then of course the colors over here correspond to the vectors over there. Now the question is, can you go in the reverse direction? Yes, you can. So let's say you have an image, then from that image you can extract the matrix or representation using a function called image data. So for example, here is a black and white image, and you can extract the matrix from it. Or here's a 3D image, slightly more general, and now you see that it's really a matrix of matrices. But be that as may, basically we reduced everything down to matrices in the world of images. So every image in some sense corresponds to either one matrix or a set of matrices and perhaps some vectors. So anything that we can do with matrices, we can do with images and vice versa. But of course, this course is about matrices. So let's now talk about how one can use our knowledge of matrices to do data compression. And so now we'll talk about SVD, singular decomposition, and data compression. So here's a matrix. It's a very carefully chosen matrix, a very nice structured matrix. If you go down steps of 0.1. If you go across, you go up in steps of 0.01. Now you might argue that's a very simple matrix, but well, in the real world, data does correlated. So here over here, you have a nice correlation-filled matrix. So what we do next is to compute the singular value decomposition. And the middle number over here, middle entry, sigma, is actually a matrix, which is the diagonal of that gives the singular value. So diagonal entries over here are 5.7 roughly, 0.14, etc. And notice that there are in fact only two non-zero singular values in this case. So what I can do is I can kind of define a compressed matrix which makes use of those values to compress the data. So you have the compressed function of k, and k corresponds to the number of singular values in vector which you take out from here. So if I take k equal to 1, I take one singular value and the corresponding singular vectors, etc. Now, if I do that with compressed 1, then you see I get back a pretty good approximation. It's not terribly bad because, for example, this is 0.99 and that's 1.00. But as soon as I change the 1 to 2 and reevaluate, you get back exactly the original matrix. So in this particular case, because you only have two non-zero singular values, you can actually do a very nice piece of data compression and reduce the rate from 100 numbers for the original matrix to around 40 numbers for the compressed matrix. So that's data compression using SVD. Basically, you take a few singular values, and because they're arranged in the decreasing order, the first few will hopefully give you a very nice approximation. Now, having set up all this background over here, the next thing is to select an interesting real-world image to do that. But when I thought about it, I said, let me take an image which is somewhat related to the course. So in this course, we talked about eigenvalues, eigenvectors, singular values, etc. So I'm going to take up an image which actually does have some interesting connections with eigenvalues, and that is about the so-called tabla from North India. So first of all, some background about maths of drum heads. So if you have a drum, then the frequency at which it can vibrate are given by the eigenvalues of the Laplacian for its drum head. So Laplacian is just a kind of differential operator. You don't need to know all that, but in future you might do some more calculus, let's say, and then you can learn about what's called Laplace operator. Okay, so basically frequencies for a drum are related to eigenvalues, but most drums in the real world actually have a uniform circular drum head. They're nice and round, and these drums cannot on their own produce pleasant sounds, so-called harmonics. Now, I've been playing tabla for quite a long time, since high school, and I can tell you that the tabla has got wonderful sounds which it can produce. And in fact, you can tune a tabla to a particular note, and if you take a set of them, you can actually make a full musical instrument which can play melodies from it. So this tabla over here, which you see, and you can see me playing it, can actually produce harmonics, and that's because the drum heads over here have got non-uniform density. In fact, the right hand drum, which is itself called tabla sometimes, has got this non-uniformity. So you got this yellow border over here, the boundary, which is called a kinari, and that's where my finger over here is. And the central part, like the CPU of the tabla, is a black disc made of iron filings or other material, and this is where you can tune the tabla to a particular note. So when you play tabla, it can actually produce wonderful sounds. In fact, a good tabla player can attract a very large audience. So that's the tabla. It's a wonderful instrument. Well, every person who plays music will feel that their instrument is the best in the world. That's the way it should be. But to me, this is a truly wonderful instrument. And so I thought that for my image, I'm going to take this rather complicated tabla and see if I can reproduce it using data compression. So that's the image for this application session, the tabla from North India. Okay, so now let's see how we can do that. So the point is that if you have a 2D color image we saw earlier on, then it can represent a third order tensor, an array basically. And why you need the third dimension? Because you actually have these RGB channels for the image. Now, if you want to apply the SVD in this case, then you just can't work with matrices. You in fact need a higher order SVD computation to deal with those RGB channels. Now that would be pretty hard to do, but fortunately we have a wonderful website called Wolfram Demonstration website, and I found a nice demonstration on that website, and I've just adapted it to my situation, where on the left you see the tabla drums, on the right you see kind of blurry thing, which actually is going to then become the image when you do data compression techniques. So let's see what happens over here when I now increase the singular values. It relies on the singular value decomposition. Okay, so let me just run this, and as I run it, you'll see that the percentage will go up. That means you're using more and more singular values, and very soon you'll get a pretty good approximation for the image. So let's run this so-called manipulate over here, and you see that already things are getting quite nice when you get to about 20%, and if I let go on a bit more, let's say up to around 55-60%, and then stop it, we have a pretty good approximation for the original image. So that's the original one, that's the kind of compressed one, and they look pretty similar to the human eye. So magically, even for this rather complicated image of tabla, one can do a nice piece of data compression. Okay, so that's the end of this session, and the main point is that real-world data can often be represented using matrices and arrays. And because we know the SVD for a matrix, then this can be used to perform data compression in such cases. And the nice thing is that typically for real-world data, only a small percentage of singular values are needed to achieve the required data compression. So that's a wonderful application of singularity decomposition. And I'll stop over here. Thank you very much.